Good morning, good afternoon, and good evening. I'm Tom Concolino, and I'm here with our presenter, Simon Bates. And thank you all for attending Rigaku's webinar on component analysis and standardless quantitative analysis. I want to start with a few housekeeping items. So we ask that you please submit questions via the Q&A button at the bottom of your screen. And we'll be answering those questions at the end of the presentation. I won't be monitoring the raised hand function, and the chat function is not on. We'll try to answer as many questions as we can, and any questions that we don't respond to, we will respond to directly after the session is completed. If for whatever reason you're having difficulty viewing the webinar live, please note that it is being recorded, and you'll be able to view the recording beginning tomorrow. Okay, and with that said, I'll turn it over to Simon.
Well, thank you, Tom, and greetings to everybody. What we'll discuss today will be component analysis in X-ray diffraction. What is component analysis? How do we use it to understand X-ray diffraction data? And then we'll go on to investigate, is it really a standardless quantitative approach? In fact, it's a fundamental parameters, standardless quantitative analysis approach to X-ray diffraction. And then finally, we'll be applying that to some complex pharmaceuticals to see how it all works out. So why is this important? Why do you even want to know about component analysis? Well, if any of you have ever tried to perform traditional quantitative analysis as solid form mixtures, you realize that it's not that easy. In fact, it's quite tricky. And for me, the most difficult part is that you have to make standards. And then there's all the mixing and weighing errors and the challenges of making standards. And then if you have to make a limit test sample, making something at very low levels is extraordinarily challenging. And then once you've gone through all of that, more often than not, your standard materials are not representative of the actual material being analyzed. So the ideal has always been to come up with some form of standardless quantitative analysis approach that's representative of the real materials that you're going to be studying and is relevant to the real materials. So that's your drug products, the intermediates, whatever it is you're analyzing. You want a method that's really representative of the unknown materials. So this is where we come into component analysis, and it really does offer a solution to that problem. It truly is a standardless quantitative approach based on fundamental parameters. So what are these components and what do they look like? Well, in X-ray diffraction, if you shine an X-ray beam, let me just turn the laser on here. If you shine an X-ray beam into a sample, and the sample is a mixture, in this case, let's assume it's amorphous with some crystals within it, then the X-ray powder diffraction pattern is additive in intensity. So if you have distinct phases inside a material, whether they're liquids or solids or even voids or trapped gas or something like that, then the diffraction pattern from each of those phases or components within a sample will give a unique powder pattern, a unique fingerprint, and that's what we call a component in this case. So a component is a unique pattern, a powder pattern associated with a solid phase or a liquid phase within the sample, and that they are all summed together to give the final measured diffraction intensity. So here's just an example here of indomethacin. This was nominally an amorphous material, however, it crystallized, and so we have some crystalline peaks on top of this amorphous component. So this is a powder pattern. It's a total diffraction pattern. Is essentially spherically symmetric that captures the independent diffraction patterns from the crystal and amorphous phases. In actual fact, if we look at that, we would normally treat them as three components that make up that data. The first of those components is the instrumental background. Now, the instrumental background scales very, very differently than the actual diffraction signal from the sample. So in component analysis, and in fact, for all total diffraction analysis, it's really important that you understand a model or measure the true instrumental background for your instrument. So in this case, the instrumental background is in green, and the red signal here represents a measured amorphous diffraction pattern. So this is one of the components. In this case, we've measured it as a pure amorphous phase of indomethacin. And in blue, we have the second component. This is the second measured diffraction pattern. This is of the crystalline component. So in this particular case, we were lucky enough that we had pure forms of each of the components that we could measure. We could derive and calculate a background in green. We had a pure amorphous sample that we could measure, and we had a pure crystalline sample that we could measure. So these are measured components that we could, in principle, use for our component analysis. Now, in reality, well, to do the component analysis, we take the two measured components, in this case, the crystalline, the amorphous, plus the background, and we just fit them to the measured data of the unknown material. This is done typically using a least squares minimization approach. And in actual fact, you can do this in Excel. So if you have your measured reference components of all the solid phases or liquid phases in your sample, if you have pure forms you can measure, and you have a measured baseline, then in principle, you can do this type of component analysis where you fit those measured components directly to the measured data. And this is just an example of that. This is actually performed in SmartLab Studio 2. And you can see here the RR factor is about 1.4%. So at least statistically, the fit is considered to be reasonable. Although we see that it's not a perfect fit, there are some areas it doesn't quite fit exactly. Now, for most real materials, it could well be that you're not able to get pure reference components. You know, a lot of the time you're working with intermediates or tablets with multiple components in there. And it could well be that some of the polymorphs you want to characterize, you can never actually isolate them in a pure form. They always come in mixtures, or you may have an amorphous form that's very unstable and it crystallizes pretty quickly. So it's almost impossible to get a pure amorphous form that you can actually collect data on. So in those cases, as shown below, we have we can do the component analysis on the measured data of the unknown materials themselves. So if you're looking at a drug product, looking at a tablet, you collect measured data on multiple batches of tablets, maybe slightly varying conditions, to generate some data that has some variability within it. Or you're looking at an intermediate, you can change the parameters there, or the concentrations, and generate multiple intermediates or multiple data sets, which we can use component analysis to extract out the individual reference components. So in this data here, I'm showing measured data collected on this indomethacin sample, going from amorphous through all these intermediate states of mixed amorphous crystalline. And then we can apply a component tool like MCR, multi-curve resolution. The one I prefer is ALS MCR, so alternating least squares multi-curve resolution. And that allows you to extract out the individual components, the basis components that make up the variability between all of the data sets themselves. So if we take this data ensemble, which is an artificial data ensemble for indomethacin with various crystalline components, amorphous indomethacin with various degrees of crystallinity in it, the ALS MCR program, as implemented in R, again, that's a free statistical platform. The ALS MCR is a library that you can just plug in and run. I find that to be one of the more useful ones that's freely available. And it identifies potentially 4 individual components that describe those range of samples. And again, if you did this on a tablet, where you'd introduce deliberately some variability in the production process, this same approach will pull out the components, the real diffraction fingerprints, the total diffraction fingerprints related to that variability within the tablet. So if you're changing the API concentration in the tablet, for example, the API loading, that's the component that typically would be pulled out. So in this case, it pulls out 4 individual components, and 2 of those are amorphous. So it's telling us that the amorphous form is slightly changing. The change at this low angle halo most likely related to changes in the moisture uptake, the humidity uptake within the sample itself. And we have 2 crystalline components in green and orange. And these have same peak positions, it's essentially the same powder pattern, but the intensities vary quite dramatically. So this could be, for example, preferred orientation. As the samples were mixed, the pure form tends to have more preferred orientation than the mixed samples. And so the component analysis pulls out those extremes of the crystalline powder pattern. Once we have those, we can do the same thing. Again, you can do this in Excel. You do the total pattern fitting with the instrumental background, and then the two amorphous components and the two crystalline components. And we end up overall with a much better fit to the data. And we would expect that because these are components that are extracted from measured data sets of the mixtures themselves. So we talked a little bit about component analysis and what it actually is, and how we can go about getting components to analyze our data. And yes, this is a total diffraction approach. We're not doing any data analysis. We're not looking for peaks. We're not doing any modeling at all. We're taking the total measured data as is and building it into our model. But how is this a standardless quantitative approach? What I've talked about so far, you may think is really quite obvious and straightforward, but how does this help us with quantitative analysis? Well, this comes to the conservation of intensity rule. It used to be called Weinstein's law, and in the past has been called Debye normalization as well. And in its basic form, what it's essentially telling us is, if you shine X-rays onto the same mass of the same material, for example here, aspirin, and they're illuminated by the same intensity source, then the total diffraction intensity from the sample will be the same and independent of the sample solid form. So it doesn't matter whether our aspirin is liquid, whether it's crystalline, it's amorphous, it forms some weird quasi-crystal mesophase, it makes no difference at all. The total diffraction intensity, the total diffracted area from that sample, it will be constant if you have the same mass of material involved. And this is the conservation of intensity rule. It only really depends on the electron density within the sample itself, as we'll see as we'll go through these examples. So you may or may not believe that, but it is a fact, and you can test it. And this is data collected on such a test. If you take indomethacin and you put it into a silicon low background holder, and you collect the data of the crystalline indomethacin here in blue, this is background subtracted in this case, and then you melt the sample in the holder and form a glassy material, or even you can do it while it's hot as a liquid. You can recollect the data again, and you'll get the amorphous form. And when you compare the total area after subtracting background, you'll find that they are essentially the same. So this is a practical demonstration of the conservation of intensity. So the same mass of the same material will give the same total diffracted area, independent of the form of the material, crystalline, amorphous, gas, I guess even, I mean, it could be gas as well if you could get it all packed into the sample holder. Liquid, it really makes no difference. Now, in reality, in making samples, it can be very difficult to control the mass. If you're comparing materials that are lyophilized, for example, with spray dried or some sort of fine milled material, they're going to have different bulk densities. So when you pack them in the holder, it's almost impossible to control mass. So the next step to that is we accept that we can't control the mass in our quantitative analysis or in our process, but we measure our total diffraction signal, and after subtracting the background, we scale them all to a common area. So this is every measured data set. So we can't control the mass. So we subtract the background from the measured powder patterns from the total diffraction pattern, and we scale the area of the diffraction signal for each of these samples to have the same total area. So we're basically enforcing the conservation of intensity law. And so although we can't control mass, we can actually scale all of these to 100%. And so we assume because they have this common area that they effectively represent 100% concentration of those materials. So this is the beginning point of standardless quantitative analysis. So now we go back to the first example where we fit our measured components and we fit them to the data. We have different scale factors. You can see the crystalline pattern is really quite small in blue here, lying on top of the background. Its area is quite low compared to the amorphous signal in black, which is more or less following the whole diffraction pattern. And the amorphous signal has a huge area within it. So if we compare those two areas together, we can straight away calculate that this is probably around about 2.7, 2.8% crystalline material in amorphous. In actual fact, this was mixed at normally a 3% weight spike. of crystalline into amorphous. And really, this total diffraction approach, in my experience, is the most accurate and reliable way of getting very, very good results for crystallinity or amorphous crystalline, or quantifying samples that have multiple amorphous components, or complex drug products with multiple components. Really, without calibrations, without standards at all, you can get quantitative results of this degree of accuracy without too much problem at all. It's a very robust approach. Now we go on to the second example, where we had 4 components that were generated by the ALS-MCR approach. In this one, when we do the fit, again, we just go through the areas. So I combine the 2 areas of the 2 amorphous components together and the 2 crystalline components together. And now I get a predicted crystalline content of about 3.15% weight against our nominal 3% weight. So really, no matter how you approach this with reasonable components, you start to get very accurate and reliable quantitative results. And part of the reason is that we're dealing with area and not individual peaks. Because if you look at the way that this is the fit to the measured data, you'll see some of the peaks are not fit that well at all, not fitted well at all. And in occasions, sometimes the amorphous component is not really fitted in the perfect way that you'd maybe like to see. But because it's based on total area and it's based on a least squares approach, it doesn't really matter so much if some peaks are overfit and some peaks are underfit, because what's important is the total area, which will still be representative. And again, as an area-based method, it's relatively insensitive to a lot of preferred orientation issues, or slight mixture issues that we might have in the material. So it is extraordinarily robust as a technique. Now let's apply it to something more realistic. A typical example we come across is we're making amorphous material. We want it to be amorphous, and we find a small peak in it. And of course, the first thing that your boss is going to ask you to do is they want to know how much crystalline is that. Now, again, this approach is very useful for answering questions like that. You generate your components in the same way. They can be either measured, or you can extract them out of complicated mixtures. And then you just do the normal fit to the data. So this is the example using the 4 components extracted using the ALS-MCR. We fit it to the data. And you can see in the zoomed image that we are picking up and fitting to that small teeny-weeny crystalline peak. And it returns a predictive value of about 0.4% weight crystalline material. And this illustrates again how easy and simple it is to set these methods up, how robust they are, and how you can apply them for a broad range of everyday problems that you're going to be facing in the laboratory. And here our goodness of fit, the R value is about 0.8%, so this is a pretty good description of the measured data. And again, you see in some cases it's fitting peaks that don't actually appear in the data, but the quantitative results depend on total area and not how individual peaks themselves actually look, or how well that they're described in the model. So based on that, we can now do a quantitative analysis. So this is a standardless quantitative analysis on all of the data that was fed into the model in the beginning. And we can plot the predicted concentrations of the crystalline component to the nominal values of the materials that I mixed up. So on the x-axis, we have the nominal weight of the crystalline components. And then on the y-axis, we have the predicted values after running the component analysis on the measured data itself. And as you can see, this is a very, very linear response curve. Again, this is not a required calibration or anything like that. This is just testing whether the standardless results that are coming out are actually representative of the nominal mixtures that we produced. Now, this methodology has a built-in reality check within it. If your component model is defined correctly, and if you've made the materials correctly, then the slope of the line should be 1, and it should pass through 0. And so it's always good in any quantitative approach you have a reality check that your model you're using to analyze the data actually makes sense, and that the numbers coming out are realistic. And in this case, the slope is extraordinarily close to 1, and the fit in here is passing through 0. So this tells me that this is a very well-balanced model. The model is correct, it correctly reflects the materials itself, and that these quantitative values are reliable.
Hey, Simon, why don't we launch a couple of polls here, and you can catch your breath.
Sounds good.
We're going pretty good here. So the first question is when's the last time that you performed quantitative analysis? And so if just kind of curious what everybody's doing, how many of you are doing quantitative analysis and how often you do it. And so you know, if everybody could just take a second to chime in, give us a feel for you know, who is attending essentially. And I believe Stephen will be able to see those results, and
Yes.
we'll take those answers for a little bit, and then Stephen can show those results.
Mm-hmm. All right, guys. And then we have a follow-up question as well.
So what's the answer here to question 1, Stephen? Unfortunately, I don't see the results. So can you display those results for us?
So the results are showing that 82% of everyone on here has participated. 2% say today, 6% say this week, 15% say this month, 35% say this year, and 42% say never.
Interesting. Okay. So hopefully everybody's eyes are getting opened to kind of how much easier. There we go. How easy quantitative analysis can be, in fact. And then we've got one more poll here before Simon goes into his final batch of slides.
Yes.
There it is. And so, of course, is what type of analysis are you doing? X-ray diffraction, Raman spectroscopy, X-ray fluorescence spectroscopy, other, of course, doesn't all have to be X-ray based. Or so we're just curious where everybody is from as well. And Stephen will give us an answer after a bunch of you have signed in. Oh, that's fantastic. So 90% of you are doing diffraction. Does that mean 91% of you are our customers? Be great to know. Okay. All right. So with that, we'll let Simon, you've got another half a dozen slides or so, and then we will get to question and answer session. So if you would go on and you can finish up.
Sure. Actually, Tom, I'm going to answer one of the questions that came in already.
Okay, you want to answer that one now?
I think it's important.
Okay.
From Alexis, that they ask, how does this compare to the direct derivation method? This is essentially the direct derivation method. You know, I've avoided focusing on specific Rigaku tools and try to keep it more general, but this is the direct derivation method. And as you go into it in more depth, hopefully that'll become clearer. So the question is, well, we've demonstrated components. We understand what they are. We can measure them, or you can actually calculate them if you have single crystal structures. You can extract them from complex mixtures. My preferred approach is to always extract components from real mixtures, so tablets, intermediates, real products that you're going to be working with. I really don't like doing it from measured pure forms because they introduce other errors like additional preferred orientation. You know, your reference materials might not be representative of actually what comes out of your production process itself. So the preferred approach is work with the production materials themselves, and then use MCR component analysis to pull out the reference components before going into then the total pattern fitting, total diffraction analysis, and working out the quantitative values. So we're now going on to investigate how this can be applied to all sorts of different materials. The first example was sort of easy. They're all indomethacin, so the amorphous and crystalline were the same material. So what happens when you want to apply this to different materials? And what comes in here is what we call the intensity scaling law. So if you have X-rays coming in to sample 1 of one type of material, X-rays coming into sample 2 of a different type of material, how does the total diffraction intensity compare between those materials? Again, assuming you've got the same mass of material in the holder. Well, it turns out it scales according to this equation here. It's the sum over the formula unit. So if you have, indomethacin, for example, you sum over the number of carbons, oxygens, nitrogen, hydrogen within the indomethacin, chlorine, for example. You sum up over that whole formula unit. And what you're summing is F squared. And F is the atomic form factor. Now, that all may sound rather complicated, but in total diffraction world, you can approximate F by its value at Q equals 0, which is the number of electrons in that atom. So, for example, F squared for hydrogen, the F there is going to be the number of electrons in hydrogen approximately, which is 1. So F squared is 1. And for oxygen, let's say we've got 8 electrons, so F squared is going to be 64. So if you compare hydrogen to oxygen, oxygen will generate 64 times the scattering intensity than hydrogen does, just as an example. And this is a scaling law that you can apply between different materials, or if you have mixtures between different components of the mixtures, you just do the sum over the squared electrons in each atom in the formula unit per unit volume. So again, it's normalized to unit volume. As I mentioned at the beginning, it's sort of related to electron density, but not quite, because it's the square the number of electrons per atom, and then summed over all the individual atoms themselves. So this is the intensity scaling law. This is the heart of direct derivation that allows it to be applied to a broad range of materials. It's a very simple formula, but it works out very, very well. So let's go on to look at a much more complicated example, a very complex example. And this is a mixture of lanthanum carbonate octahydrate with cellulose. Essentially, the way I look at this is that cellulose is like the amorphous matrix, and we're mixing in lanthanum carbonate octahydrate into that matrix. Now, if we compare the scattering efficiency or the scaling intensity between these two materials, lanthanum carbonate octahydrate is about 21.1, cellulose is about 3.3. So there is a difference of about 6.3 in the scattering efficiency, if you like, or the intensity scattered per unit volume from these two different materials. Now, it turns out that in addition to this large difference in scattering intensity or efficiency, this is an extraordinarily complex system to work with for many, many reasons. One, it is difficult to mix. There's very different flow properties between the materials. One of them tends to be more staticky, one clumps up. So they are challenging to mix in the first place. As I mentioned, we had this large difference in scattering efficiency. In addition, there is a huge difference in the absorption length of the X-rays that the copper X-rays we're using to illuminate the material. In fact, greater than a factor of 10. And this actually introduces really an interesting complexity into the problem. For example, if your mixing is really very bad and all the lanthanum carbonate is sitting on top of the sample, then if that's like more than a couple of microns thick, then the X-rays will not penetrate through it to see the cellulose underneath. So in that case, even though you may have just a small amount of lanthanum carbonate in there, if it's all on the surface, then you'll measure that to be 100% lanthanum carbonate with no cellulose. So it has those additional complexities, which is called microabsorption in that case. The lanthanum carbonate exhibits preferred orientation. It exhibits strong preferred orientation. So depending on the pressure you use, the amount of it's used in the mixture, you're going to get very, very different responses. And it's also a variable hydrate, just to make it even worse. It's an octahydrate as delivered or as received. But when you mix it in with other excipients, it exchanges water with the excipients. It can lose water, it can add water, and so that changes the lattice. So the lattice breathes. So it has all sorts of variability and complexities in it. And we truly wanted to pick the most complex example we could find to test this methodology. So we collected, in the end, over 100 data sets on this system. We targeted 4 concentrations and we mixed multiple aliquots multiple times So we could capture the full statistical variance associated with mixing. So we could estimate if we were really using these data as standards, what sort of error will be actually introduced into the method itself. And we passed it through the ALS MCR. And by the way, on the reference materials, you'll find a reference to the ALS MCR and some other papers associated with multi-curve resolution. So I encourage you to read through those references to learn more about it. And also on the direct derivation, the original papers associated with that are also listed as well. So you can go and read those at your leisure. So in this case, we extracted out 4 components again. One of them is for MCC. So the microcrystalline cellulose is essentially stable. It doesn't change very much. We used Avicel 101, so it's a known excipient, very well behaved. Only a single component associated with that. The lanthanum carbonate octahydrate has many components. So we picked out 3 of them. As you can see, there is a huge variability in the signal from the lanthanum carbonate. It's just astonishing. You know, this broad peak cluster here, you can see how the intensity changes here. The very sharp low angle peaks. In one sample, it came all the way down here. So there's a massive variation in intensity. And even the appearance of the patterns are quite different. So clearly, this is going to be a complex problem for us to try and resolve. So we go through the analysis. Here's just one example of one of the patterns that we fit. So the overall data fitting is really good in this approach. And this is a summary of all of the 100 data sets that we actually crunched through. So we picked 4 concentrations, 20%, 40%, 60%, and 80% of MCC. And these are across the different aliquots. So you can see how the quantities or the predicted values from the direct derivation or the component fitting method give a massive variability in the actual concentration of lanthanum carbonate in these materials. And it's the same for pretty much all of the ones that we mixed. As we get to much higher concentrations of MCC, then the spread in the data seems to be somewhat less. But certainly at the lower concentrations, we have substantial mixing issues. Now, somewhere in there, you'll see there are little green dots, and these green dots represent the average data. And you can see the calibration line essentially, well, not the calibration, the linear response line more or less tracks through the average data sets across these. And really the icing on the cake are the red dots. These are done through wavelength dispersive XRF. This is a fundamental parameters model that we ran in XRF, which is a very well-established approach in X-ray fluorescence. We just took one aliquot. So, and from that one aliquot, from each of these mixtures that we measured, you can see that the fundamental parameters XRF essentially follows the data that we've extracted from our fundamental parameters component analysis. And I think this really helps to illustrate or reinforces the point that this is truly a standardless quantitative approach. It's a fundamental parameters approach. The only thing you need to know about the material is the formula units, or the molecular formula unit, or what atoms per unit volume. That's all you need to know. And then you can go on and do standardless quantitative analysis. So we now have fundamental parameters total diffraction and fundamental parameters XRF to do our quantitative analysis. So to summarize, we've reached the end of the slides. What we've discussed is what is component analysis and X-ray diffraction. We've also gone on then to describe how is this really a standardless quantitative analysis. And I hope I've illustrated that now. How it works is based on the conservation of intensity laws. And it's a very robust and powerful approach for standardless quantitative analysis. And we've shown some applications to complex pharmaceuticals. So at that point, Tom, that brings us to the end of the questions and answers.
All right. So obviously we do have time for a Q&A. Stephen, if you would launch the final poll, this is going to be our launching point for the Q&A. So what we're asking is, what are the biggest challenges you've experienced in your quantitative analysis? And you can see there really is only one answer. And so we'd love to hear from you in the question and answer session here, in the questions, not the chat, because I can't do anything with the chat. And choice two, of course, isn't really an answer. So, so we'd love to hear from you on the front, in the question session here, in the Q&A. So we welcome any comments there. And our first one is, Simon, is from Bo. And it says, how do you do the ALS MCR analysis? And do you have a recommended software package?
Yeah, the package that I would normally use is the one that's in the R statistical environment. I like to use R again. It's a freely available package. Anyone can access it. It's independent of what X-ray system you're on, whether you're on a synchrotron or wherever. And in there, you'll find that there are many multi-curve resolution packages that you can use. Now, the one I use, the ALS one, is an older package, so you have to install an older version of R to get access to that package. But I found it to be the most reliable approach to extracting out components and measured data. There is somewhat of an art to do it with the third-party package, and if any of you want to undertake that, I'm happy to go through it with you. So just reach out to me and contact me, and I'll take you through it step by step. So if you have data you're trying to do this on, you can also send me the data, and I can use the same approach for you. Outside of that, Rigaku is introducing the same type of MCR approach in the SmartLess Studio 2 software. So that will be available, I believe, in September. So this is a pre-launch event in some ways of we'll have our own package in the SmartLess Studio 2 software. But it is available in chemometric packages as well. It's a standard part of chemometrics and has been for some time. So if you have a chemometrics tool in-house, it's quite possible you have MCR in there. But the difference between like IR approaches or Raman approaches and X-ray is you really have to extract them in real space, so not variant space. So you want to have your components to be real diffraction patterns. Otherwise, the direct derivation last step or the component fitting doesn't work as you sort of expect.
Okay, all right. So we actually had the same question come in one after the other.
Yeah, I saw that. Yeah.
Can you explain kind of the difference between Rayfeld and direct derivation?
Yeah, we've got some mind readers out there. So, I actually had a slide on that and I took it out because I wasn't sure how many people would know what Rayfeld is. Well, in some ways it's similar in that it uses a whole pattern fitting and least squares to fit the data. So in that sense, it's similar. But on another sense, it's really very, very different because Rayfeld is based on a Bragg approach, which is definitely not total diffraction. Now, Bragg is not really compatible with a total diffraction type concept. So the total areas you get from the Bragg approach are absolutely not related quantitatively because you have to put in so many parameters that are not related to the material, things like the peak shape, the peak width, and it goes on endlessly, the parameters that you have to define in Rayfeld in order to fit the data. And those parameters are not related to the material at all. More than that, particularly when you're dealing with organics, organic materials contain a large amount of defects. It's just a natural part of what they actually are. And that is absolutely not modeled in Rayfeld at all. So if you do a Rayfeld fit to the data, it only fits the perfectly crystalline parts. Even if you broaden the peaks for a small crystal size or microstrain or something, it's really only modeling the average coherent crystal structure. And real organic materials are a lot more than that. They are the defects that they contain, the thermal vibrations. There's a lot of things that are inside those materials that actually define their fingerprint that are absolutely not captured by Rayfeld, but they are an inherent part of this component approach. They are contained in each component. This is really a true fingerprint. It contains the defects, the thermal anharmonics, maybe even the Compton scattering. So it's a more complete fingerprint of the data. Now, the DD method as implemented in SmartLess Studio 2 does allow you to define a crystal structure as a reference. And you can do that and you can fit the data very well. But when you compare it to the true total diffraction approach, it underestimates the crystalline content by quite a lot. Because in some materials, maybe 30% of the diffraction pattern is due to defects for organics, with the raised background levels and things like that. So it's similar to Rayfeld, but different. Rayfeld has lots of variables. lattice parameters, peak widths, and things like that. This approach, this total diffraction approach, only has two for each reference component. One is an offset in 2 theta, and 2 is a scale factor. So again, it's much more robust, simpler, very fast. We have an automated approach in SmartLess Studio 2 that can do about 1,000 data sets in a minute in terms of fitting them with the DD method. It's extremely fast. ReapVelt takes much longer to fit data because it has so many variables to model.
All right, very good. Okay, so let's look at this, the next comment here from Adedayo. And he's curious if this can be applied to pure crystalline polymorphs rather than the amorphous context, right? So
Right.
For preferred orientation, right, which is also tends to be a limitation when you're doing ReapVelt, if I remember my old data processing days. And then the area, this total area normalization, right?
Yeah.
So,
Yeah.
Comment on that.
Yeah, before I answer that, I saw that the amorphous was written in there. I forgot to mention that. Of course, ReapVelt really struggles to describe amorphous materials. And so if you have, multiple amorphous components in a sample, it can be extraordinarily difficult to do that with ReapVelt. Although there is the Ponks addition to ReapVelt that does help you with a well-defined amorphous, it's a pain, and I don't recommend it.
We'll have to define it.
Yeah. So not recommended.
Yeah.
So back to crystalline, yes, it absolutely can be used for crystalline. If you read through the original DD papers from Hideo Toraya, you'll see that almost all his examples are crystalline materials. And most of the time that I apply it, I use it on all crystalline components. There's just a few areas where we're dealing with multiple amorphous phases. So yes, it does work for pure crystalline, works in the same way. It's very good for preferred orientation. Because if you do the MCR approach, you'll get like 2 or 3 reference patterns that will capture the extremes of preferred orientation. Now, if it's just a plate or a needle, that's pretty easy because you get like 1 component in the preferred orientation. But if it's sort of cuboid in shape, then you may have multiple components in the preferred orientation. So then you're going to need multiple reference components, and the MCR can pull those out. So it does capture that. And as I've mentioned as well, you don't need to get a perfect fit to every single peak, because it's not the individual peak intensities or how well you fit one peak. What's important is how does the total area fit. And with preferred orientation, some peaks go up and some peaks go down. Now, there is a caveat there. If the preferred orientation is so extreme, like you have a single crystal, for example, then on a powder measurement, you can't capture that total spherical symmetry. It's broken. So if you really break the spherical symmetry, then the approach does not work at all. But if, let's say, you have an area detector or an imaging detector that captures part of the Debye ring, then you are really robust to preferred orientation when you do apply this to a broad range of crystalline materials.
So the next one is a max and min measurable quantities. So have you tested those limits?
Right. I haven't really tested the maximum amounts it will look at, but as you saw from the response plots for both of the mixture examples I gave you, they go up to 100%. But I haven't gone through and tried to pin that down to how close to 100% can you go. But on the other hand, on the limit, the lower limit, then there's been a lot of work done on the lower limit. And we ran a broad range of amorphous drug products, for example, with multiple amorphous components, and we're able to achieve LOQs between 2 to 4% weight of each amorphous component. This is on a general drug product. On very specific cases, even for amorphous, we've been able to get down below 1% LOQs, even for amorphous materials. For crystalline, obviously, you can do much better. The example I showed you was about 0.2, 0.4% a crystalline component in that amorphous material that crystallized. We've done many tests down with LOQs down to 0.1%. And if you're willing to collect data for a longer time, then you can probably push it much further beyond that as well. So just in the end, it comes down to how long do you want to wait to collect the data.
Okay. All right. The very next question is this technique applicable for cement or iron ore, right? So various others, and then again, the expected accuracy in LOQs. And so I think a little bit of that, but yeah, beyond pharmaceuticals.
Absolutely. Most of the methods that I've developed for this for various clients have been in cement. So it's very applicable to cement, particularly in some of the new green cements where the standards haven't really been worked out as yet. So often they have no idea what they're making. And this MCR approach is perfect when you're synthesizing something and you end up with a mixture and you have no idea what the components are, because you can extract out reference components from unknown mixtures and you can quantify them. So when you do eventually identify chemically what they are, you already have all the quantitative analysis. I actually haven't done it for iron ore, but it's definitely applicable there. Of course, if you're using copper radiation, you get a lot of fluorescence from iron. So you'd have to use either a detector with a very narrow energy window, or perhaps a monochromator system, or move to chromium radiation or something like that if you're working with iron. But that's actually an interesting problem. You could probably build the fluorescence into the total diffraction signature. And now you suggested that I want to try it and see what comes out.
In fact, right? So
Yeah.
Wrestling should be pretty easy. It should be just another.
Yeah.
Curve you're modeling as almost as another background, second
Yeah,
background.
I think that should be possible. I haven't tried that, but absolutely you can do it. Yeah.
Okay, so I'm going to skip down to another question that this comes following that is, how do you determine the background? Are you doing an empty sample holder, or is it mathematically?
Yes and yes. So for each of the instruments, we calibrate a baseline, and that is done by using silicon low background holders initially, and also silicon powder. So a combination between those two, we set up a calibrated baseline for each instrument. And again, anyone who's interested, I can take you through how to do that. So that is essentially how we do it, using both a low background holder made of silicon and silicon powder.
Okay, all right, and then we'll go back up to the top of the questions here. They're curious is how accurate is the crystallinity test? And I think part of this is not necessarily within the Rigaku software, but part of our analysis, right?
Yeah, sure. Yeah, there are many ways of doing percent crystallinity, and the numbers you get will depend on the approach you use. And the different approaches will give you different numbers. But the total diffraction approach, the one I've just shown you, the component approach, again, in my experience, gives you really accurate quantitative numbers. And I've tested it on multiple systems where myself and other people have made spikes, going to extremes really to make sure we get very accurate mixed materials. We mix in the liquid state and then crystallize them out. And the component approach is almost always bang on within 0.2, 0.3% weight, something like that. It's very, very close all the time. Now, other techniques are approximate techniques. The percent crystallinity approach, I think the one you're referring to, is based on Rouland approach, where you essentially construct a smooth baseline through the material. That, in my experience, underestimates the amount of crystalline component, and it can be off by quite a large way. But relatively from sample to sample, it's good. So if it says one sample has more and one sample has less, then that is probably almost certainly the right situation. But in terms of a quantitative number, it will probably be off from the true value.
Okay, all right. So this is a longer question. Another question. Daniel's comment here is, it's a little longer, so I'm going to read this out loud. Is doesn't have large quantities of samples, right, that are not all that stable. So it's not always possible for him to do multiple data collections and then average them out. And so diffraction angle, the peak positions can change from the standards. So I think he's asking a little bit of, is there some machine learning that can be done here too that says, I've got these shifts can occur, and can you set the material so that it starts to build its own, almost its own calibration setting based on his own material.
Yeah. That's always a challenging situation, but again, it's not that uncommon when dealing with organics. A lot of them are metastable and they'll change during the measurement. So what we usually teach people to do is we do snapshots. I mean, most of our systems come with either a linear or an area detector, and we try and teach people to take very rapid snapshots. In that case, you put the sample in and maybe you take 10 snapshots in a row, and then we have a software called the cluster tool, which will look at that and will segment it into data that represents the same type of material. So let's say you put your material in and it changes from A to B, and then you run these snapshots very quickly over a period of, let's say, 10 minutes, you get multiple snapshots. Then the cluster tool will separate the data that's essentially A and the data that's essentially B. So you'll end up with two clusters of different types of data that's essentially the same. And then those can be averaged automatically by the software, and you can use those as components. So although your material's changing from A to B, you've got a component for A, you've got a component for B, and you collect it on one sample by doing multiple snapshots over time. And that tends to work pretty good. So that's a combination of the cluster tool. As Tom was saying, it's a machine learning tool that separates out powder patterns to identify those are the same and those are different. And then from that, you can construct your own standards as well and come in. So there really are many ways of identifying components that you want to call a standard.
Okay, all right, so, all right, the next question from Adadayo is, can you buy the software? And of course you can. I would, Adadayo, if you would, you can send an email to info@rigaku.com, or you can, I believe on Simon's page, you can go to them, get some links to send some questions as well. And we're happy to chat with you about the software and that kind of stuff if you've got a Rigaku instrument currently. All right, so hopefully that answers your question, Dio. And again, we're happy to chat with you about the software. It looks like our final question, and we are kind of running up on time here, is from Mustafa, and he's asking, so from the crystal dispersed in the amorphous matrix versus crystals that grow within the amorphous matrix be different. So would that diffraction be different if it was grown within or without of the matrix?
Yeah, absolutely, Mustafa. That's one of the main reasons that we're trying to find, standardless approaches. Very often we find that you have like some purified reference crystalline material you want to use as your reference. And then you mix that into amorphous form to try and generate these synthetic or boutique standards. And very often the crystalline form, or the way it looks, its habit, for example, the degree of preferred orientation and the like, is going to be very, very different from these spiked artificial boutique samples than it will be from a crystalline material that naturally grows inside an amorphous matrix. I'm sure you've seen it yourself. You watch them crystallize, and you find just one peak comes up, and you wonder why that peak. It doesn't make any sense at all. And then for a different sample, you get another peak that comes up. And of course, what's crystallizing out in the amorphous matrix is definitely not representative of your boutique synthetic standards that you have mixed. So again, the ideal is that you extract components from the real samples. So you truly capture out how the crystal form grows, how is it different in some way. Even though it's the same polymorph, it may have a very different habit growing out of an amorphous state than it does growing out of the solvent or some synthetic crystallization you're running outside the production process. So that's really, very, very important. And I'd like to go back actually to a point you made, Tom, about backgrounds. Again, this is also fundamentally important for total diffraction. Probably the most important thing is to define an instrumental background, a calibrated instrumental background, because it does scale very differently than the diffraction response. And you go to a Rietveld program or most full pattern fitting programs, and they create these hypothetical backgrounds that are complete nonsense. That they absolutely do not represent the instrumental background at all. All they do is just chop off the crystalline peak, so you can apply Bragg's law, which is a gross approximation anyway, to the data. And so absolutely do not use standard profile fitting approaches to determining a background on your sample, because it'll skew the analysis completely. There's a lot of things that are called background that are actually real fingerprints and signal from the material. You're
fundamentally changing the way people have to think about background correction, Simon.
Totally, yeah. Total diffraction is the future.
Yeah. All right. So that's all the questions we've got. Certainly, you can reach out to Simon via LinkedIn, which is a couple slides from now. If you have questions, he'd be happy to chat with you or directly email him. Oh, well, wait, we got one more question. Two more questions jumped in.
Oh,
Let me see. We had a couple more minutes. We'll squeeze these in, and these will be the last ones. So Simon, if you know, if there's an FDA limit for percentage of API crystalline and amorphous material, I don't know that answer myself.
yeah, usually what the agency requests, if you're putting a method together to detect crystalline content in the material, that is able to detect 5% of the API content as crystalline. So let's say you've got 1% API in a material, there should be amorphous API. The agency wants you to detect down to 5% of 1%. So that's a very low level of crystalline they'll want you to detect to.
Okay. All right. And then this final one is actually is Dan would like a copy of your presentation with the reference articles. This goes right up to the very following slide here. So Dan, in response to you, a recording of the webinar will be available tomorrow, and an email will go out to all of you who've registered with instructions on how to view that recorded presentation. And you can certainly reach out to us directly if you'd like to kind of get a look at Simon's slides. I think you can share most of these slides, Simon, is that correct?
Yep, absolutely, yeah.
Okay, and he'd be happy to review it with you. Links to those the resources that Simon mentioned, and that's again what Dan is asking in his final comment here, they'll be on the landing page as well. And so that will all be coming out in an email tomorrow. With that said, Simon, if you want to jump onto your next slide, if you want, you guys want to connect with Simon directly, he is on LinkedIn. It's Simon Bates. And he'll be happy to have kind of continue these conversations directly on the phone, etc. So please don't hesitate to contact him. And finally, final slide, Simon, is we just want to thank you all for spending an hour with us. We will be having a second session. I have to leave it to Simon for what that title is. I can't remember it off the top of my head. But there will be another session, not on this topic, but on more general topics in diffraction. So we thank you all for your time and have a great afternoon.
Yep, thank you all, and goodbye.